Hi everyone, my name is Jean, and I'll be giving you a short preview of how to optimize cluster-based randomized experiments under monotonicity. These are the authors of the paper from the left, Jean, the one narrating the video, Vahab, David, and Edo. Imagine someone asked us to group these authors into pairs in a meaningful way. There are several heuristics we could choose from. For example, David and Edo are both profs at Harvard, and Jean recently interned with Vahab. But it is also true that Edo is Jean's advisor. In practice, different heuristics lead to different pairings. It's not always clear what is the best way to cluster units together. Let's now try to understand the context for why we wanted to group these units together in the first place. The context is randomized experiments, also known as A/B tests. Imagine we wanted to understand the effect of a vaccine on a population. In other words, we want to compare a world where everyone is vaccinated versus a world where no one is. Since we can't both vaccinate everybody and nobody at the same time, we run a randomized experiment where we assign half the units at random to be vaccinated, and the other half to stay unvaccinated. If everyone is independent from everyone else, then in expectation we recover the true effect of the vaccine. But it's not always clear how to analyze these randomized experiments when interference is present. In the case of vaccines, for example, units are not independent. Imagine a graph of units that can possibly contaminate one another. Under the left assignment, David is vaccinated and in contact with an unvaccinated unit, Edo. And in the right, David is still vaccinated, but since Edo is now also vaccinated, David is no longer in contact with an unvaccinated unit. David's outcome is different in each case, even though David's treatment stayed the same. One way to make the experiment better, therefore, is to assign units in groups so that we avoid situations where vaccinated units and non-vaccinated units interact. This is the original motivation for finding good clusterings of our units. As we saw in the beginning, it is not always obvious to find a perfect clustering. Say two experts give you two different clusterings. Which one would you choose? Clustering 1 or clustering 2? In general, it is difficult to choose between the two of them without a parametric model that exactly captures the interference between all units. There is one condition, however, under which we can answer this question, which we call monotonicity. It is intuitive that a vaccinated unit that is surrounded by other vaccinated units is less likely to get sick than the same unit if it were only partially surrounded by vaccinated units. Similarly, a unit surrounded by non-vaccinated units is more likely to get sick than a unit partially surrounded by vaccinated units. Note that the comparison between the top row, the most extreme situation, corresponds to the true effect, the estimator that we're trying to estimate. In practice, however, we make the comparison with units on the second row, and this difference is always smaller, following from the previous intuition. In other words, we always underestimate the true effect. With this observation in mind, we can go back to our original question of which cluster-based assignment is better. Say that we can observe both the outcome of clustering 1 and clustering 2. The outcome of clustering 1 is lower than the outcome of clustering 2, and significantly so. Without even knowing what the estimand is, we know that clustering 2 is less biased because we know that they both underestimate the true value. Of course, in practice, we cannot get both estimates at the same time. In our paper, we show that we can still exploit monotonicity using an experiment of experiments design. We then explore certain reserve price experiments and show that they are monotone. Thank you for listening, and see you at KDD 2018.